spatial theory. So we, at the moment, now we consider M on the Hilbert space H. And it comes with that automatically you have is the commutant for normal algebra. Now, what happens is, in this circumstance, okay, H can be just an arbitrary, just a faithful representation of normal algebra M. No, need not to be cyclic, no standard. So, but what happens is the following. If you stay fixed phi, W naught of M, and the psi prime is of M prime, that both faithful semi-finite normal weight. One is on M, the primed one is on N, M prime, M prime. Then they exist uniquely indeed, though the uniqueness, to claim uniqueness, you need a mode side condition, which is then we have to spend another hour or so. So we need simply state necessary property for us is this self-adjoint operator called d phi d psi, which is non-singular self-adjoint positive operator on H, which acts following way. D phi, this is a way, d phi d prime of IT x d phi d prime prime minus x, it will be sigma phi t of x for x in M. And d phi, same operator, the minus I, or maybe, or minus ity d phi d psi prime it will be sigma psi being faithful semi-finite normal weight, so it has its own modular homomorphism of psi prime, or applied to y for y in M prime. So this spatial, Alan Kohn called this as a spatial derivative. Phi relative to psi prime. And indeed, if you reverse it, d psi prime d phi is indeed d phi d psi prime inverse, precisely inverse, non-singular self-adjoint, so it has inverse. Okay. Now, this is the key ingredient to glue this modular cross-section algebra, or the integral level 1. Okay. So we need a little bit more for the preparation. Okay. To work on the Hilbert space, it's M prime on the left. This was also octet on left. it is rather cumbersome if you use it all the time from the left. It's commutative. So instead, we consider the opposite algebra of commutant. Opposite algebra, namely x, y circle equal the other set, the same set, but the product is reversed. Okay, it is a polynomial algebra. Everything is the same, reversed. Then what is gain? Now, n acts on h from the right. So instead of y prime xi, we write it the xi y prime circle from the left, from the right instead for y prime in y. Well, it says the prime is order a bit cumbersome, so. Or opposite is either way, so you can write that way as well. So in that case, y is in n. Okay, the commutative property of m and m prime becomes as associativity of the left action, right action. So x psi y equal to x psi y, for instance. So that's the commutativity of an m and m prime, and the n is acting on that. Now we are the all players. We are now talking. X is now real line plus the set of all semi-finite weight and Hilbert space and set of all semi-finite weight. Okay, and now for the psi in we write psi opposite the corresponding weight on the m prime. So we write so we have the element here r phi xi and the psi are the point, and I'll say everybody 1. And the equivalence relation T fixed, just like yesterday. 2 R2 phi 2 eta xi 2 psi 2. Okay, the membership is R1, R2 are real number. Phi1, Phi2 are faithful semi-finite normal weight on M. Xi2, Xi1, Xi2 are element in H. And the Psi1, Psi2 are element in W not N. And the relation is the following. D Phi1. Okay, remember this one is weight on N. Spatial derivative is relative to the weight on N prime. So we consider opposite of that. Psi 1, d psi 1 circle of power R1, psi 1 equal to d phi 2 d psi 2 opposite of IR2 applied to psi 2. Now we relate the psi 1 and psi 2 according to T. D psi 2, D psi 1 sub T. Okay, this is the relation tilde. Each time, it depends on this T. Very strongly depends on T. Now we define, and you prove this is equivalence relation. Or we have a chain rule. So you have they show this one. And this X divided by this equivalence relation will be H of T. H of T, not yet Hilbert space. But now we equivalence class of R1 psi or R psi equivalent psi, we call this one to be write this one as the phi to the power IR psi to the power I T minus R. This is the way to group. This is the definition. So now phi IT. So if you fix phi and psi, you have this expression. That's the ingredient. So this is the H of T is the set of all those phi IR psi I T minus R. R is in Leon line, and psi in the Hilbert space, and this doesn't matter which phi you choose. So phi in M, psi in W naught of N. But choosing other psi doesn't make any difference. You can leave this as well. Others you can use this rule. Okay, one more item was that here is the relation with conical derivative is that phi1 is related to the d phi 2 d psi prime to the power I t. Let's see which way we go. This one is phi 1 IT minus psi minus IT. So it's, I think it is d phi 1 times d phi. Well, probably on the left. I think it is on the left. D phi 1, D phi 2, the power, and D phi 2, D psi prime to the power IT. Okay, so those are the relations when you change the weight. And for the denominator accordingly on the cocycle derivative relative to m prime, the similar relation hold. So with that type of relation, and the spirit is the following. So d phi d psi d psi to the power IT, or the opposite, equal to PIT, the applied to xi equal to xi psi minus IT. Okay, that's what this is in our mind. So, with this much in mind, we can now introduce Hilbert space structure. So, okay, H of t, the vector space structure is the typical example. The vector is of lambda xi r psi I t minus r plus mu of phi to the I r psi to the I t minus r, which is then nothing but phi I r xi lambda xi mu eta psi I to the t minus r. And the inner product.
Masamichi,
Yep.
the R's can be different, right? You don't have to have the same R.
For any R, so as long as you keep the t minus r, so that this is the element in HT. For the R, I'm not fixing R. R is moving the real line.
So in the second term, you have a different
And the psi power t minus r, and the product keep in H of t.
No, I was just saying, the first term you have R.
Yeah, if you don't drop the, so say, in this one, well, of course, because you cannot really think without this one, but if you think this one looks like this is in the HR.
In the second term.
Second term is,
Plus. After the plus.
oh, this one is Eta.
And then what is the
R prime.
Should it be R1, R2, something like that?
And
No, but should it be like R1?
well, R1 was, remember that the equivalence relation is given by R1 and R2. But when you have R fixed, one of them was, this is by definition phi to the power r psi psi to the t minus r. This is our definition of okay? So the R1, R2 is mean that those are the key.
But here, in this one.
So this is the class corresponded to the R phi xi psi and t.
This one, is it the same R?
Same R of here. If R changes, then you cannot have a distributive law. Has to be same R. This R and this one has to match up. Otherwise, it goes on the wrong space.
But then the how is the addition of any two elements in HT defined?
Yes, that's exactly addition. This vector times phi to the power r psi to the I t minus r. But so exactly same form.
Actually, take for each. What do you write? R.
I to the power IR?
No. R phi
Psi xi eta. That's the
Psi.
and eta.
And psi,
Yeah.
right?
Yes. The second one is the same again, R.
No, one minute.
Then you have to
Wait.
use this rule. So that you line them up in the all phi and psi term. Okay. Another was everybody.
This is the question. If you take two things like this, different,
Yeah, if it is
then does there exist something
exactly.
else the same R which is equivalent to this?
No. This R, if you have R1, R2, phi1, okay, phi2, xi2, psi2, then unless you have this relation, they are not the same element in the space. But if you have lined them up, okay. But since you are talking of this equivalence class in T, remember that the equivalence relation heavily depended on T, value of T. So this is an element of HT. So for instance, fit the IR equal to other one, say psi, phi1 to the IR is d phi1 d phi2 to the R of phi2 IR. Okay, that's the rule we imposed on when we had at M of T. Okay? That was the rule. And if you have R1, and in that case, we need slide this one to the, in that case, if you have this just alone, they are sitting in a different M of R1 and the others M of R2. Remember, M of R1, M of R2 were considered the disjoint set. No common element in between when we have made a fiber space. So when its power is involved, this power has to be matched up in M of T. But on the Hilbert space level, since you have this concrete operators acting on Hilbert space, you have a way connect one, the distant different value. But it's because it is on the Hilbert space H, you can have those identity on the Hilbert space, not in the space of the here. And then if you have you fix T and the phi and the psi, then everybody can be written, arranged into, if you choose xi properly. And also you can choose this R arbitrarily. You don't need to fix this R. You don't need to fix this R. That those are already stated there. The equivalence relation takes care of the difference value because the concrete operator is involved. This one not disturbed. Okay? And of course, this is a little exercise that when you have R1, R2, how you write this down? Okay, this one is in this way. Is then this one. You can write this one. This one is phi R1 xi 1 equal to this equal to, you were saying phi to the IR2 xi 2 and d, no, you have here d phi 2 d psi 2 circle to the power R2 and psi 2, you have d phi 2 d phi 1 sub t. Then you can, so you have psi 1, psi 2 distinct, and this one the phi 1, phi 1 and phi 2 distinct, you can connect. Okay? And the basic rule is this is the basic rule. And whenever you see phi t, phi s, then the phi of I s plus t. That's another one. And when you have psi it, phi minus it, distinct one, this is a deep psi d phi t. So with all those rules, you can move from one expression to other expression. But all that, however, here, important fact, all those changes are linear on the level of xi. Okay, that's all linearity is expected, is respected. So this equivalence relation does not destroy the linear structure on the Hilbert space. So therefore, thus you can write the introduce the vector space structure. At the same time, you have inner product. That's if you phi r psi of t minus r, inner product phi r eta psi I t minus r. Okay, if you change this base p and psi for the each, then the formula becomes very complicated. But if you line them up, it is just psi eta. So that makes that the p to the power it to be unitary, for instance, or psi to the power it applying from the right is unitary, and indeed, yeah. Okay. So now, with this h of t is a Hilbert space isomorphic to h for each t. Isomorphic to h. That's how we did it. Now we have disjoint union once again. Disjoint union of h over t, disjoint over all real line. Now, you can have this marking from M of S times H of maybe H of R, H of S, N of T. Okay, remember this N and the NT, MT constructed yesterday's procedure here on that. So, okay, in this case, it was times psi of S times, well, this was at the same time, what was it? H to the IS psi to the, no, R times IR, I T minus R, say for, so the element is something of that, times and Y psi I T. So what you get is, then it's almost clear, this IT time plus S, so this is sigma V minus R. I think this was IR, otherwise it doesn't fit this one. On the, and H, HP, so this S minus P, because IIT, and this will be minus R plus P of X, apply, that is then, this is psi IR plus S, sigma phi minus R plus S of X applied to Xi, and also from the right, psi of, I think that, you have here the IP psi minus IP, so D phi D psi opposite of power IP, and it goes to the, then he phi p IP minus psi IP, so this is times psi and D of phi D psi evaluation at where? P, and psi is, and the psi, altogether we are adding RP or RST, I of R plus S plus T, which is then an element of element in H S plus R plus S plus T. So that's the way the trilinear operation is now represented. So, make things short, then with this trilinear, so that MR, MT acts from the either side. So you can make then the action of the gamma 1 and of both gamma 1 of f of m act on the gamma 2 of this square integrable cross section. Okay, this is the scale, the Hilbert space, the Hilbert space of square integrable cross section of this G, disjoint union of Hilbert space. So the value at T has to land in H of T. Okay, so and so the norm psi of norm square is psi of S, which sits in H of S, norm square D of S over the now real line. And natural x from here, and the x psi of S equal to integral over real x of r psi of S minus r dr. And when you observe what's happening if you have x of r sitting m of r, and this is sits in Hilbert space H S minus r, m over r times 1, this runs in, actually this, since this contained unitary, so this is H of S. So this integration takes place within Hilbert space H of S. Okay, so when you're summing up or integrating, you have to have a vector set in the same vector space. It's not that if you have disjoint place, you cannot add or anything like that. So this vector setting H of S, that is what we were really planned this trilinear operation. So the index match up. And the same with y. For cross section of, so gamma 1 of G, F relative to N. Then we are now operating from the right. So xi y of t will be integral over xi s y t minus s ds over the real. Once again, y of t minus set in n of t minus s, this sit in h of s, this combination product bring it back to h of t. So all the summation taking place within h of t integration, and we assume that the xi of s is L1, excuse me, y is L1, and the xis the L2. So the normal calculation shows this operation makes sense. And so gamma 1 f of m acts on this gamma 2g, say this one, reverse space H tilde, from the right, H tilde, and from the left, and gamma 1 of F of N acts from the right. So that Hilbert space is left gamma 1M FM module and right gamma 1 of Fn module. And the theorem states, theorem is that so we have now the following. So that pi of F, gamma 1, well, maybe the gamma 1 Fm prime is generated by the right action of gamma 1 of Fn. So opposite, so we bring it back that gamma 1 of F of N and the opposite and we close it. Because when you call it the operator, then you are operating all the time from the left. So you twist again by opposite algebra. That is precisely commutations relation. So the gamma 1 of Fm double prime is M tilde. This is the isomorphic to, if you fix the weight, then this is sigma phi over R when you fix. And this one is so M tilde acting on H tilde, then the M tilde prime is precisely M prime tilde. That's the canonical core for N. So that means this is a spatial theory. Hilbert M acting on Hilbert space, you define the core, together the Hilbert space core and H. So MH, so that means MH to M tilde H tilde is the the functor from the spatial von Neumann algebra to semi-finite spatial von Neumann algebra with trace and the one parameter automorphism scaling the trace down. Okay, and the Hilbert space came side by side. So this is the actually the way you have this. You are accompanying the Hilbert space, and you know exactly how the commutant look like. So this and so this is the I call it the core, the canonical core. Canonical. Of spatial Hilbert theory. We don't require H to be standard. So, but for the visualize, actually, you don't need to go through all this equivalence relation and anything like that. The element, the for Neumann algebra and fit the IT in generate the same core. This is your core M tilde. All right, so that's the, now I want to see the property of M tilde relation to M. Well, one theorem is this one already stated. Takesaki, M relative commutant in M tilde is center of N, and if M is this center of M is precisely the fixed point on the of the one parameter automorphism restricted to the center, and if M is if M is a factor, then this is the scalar, which means that action is the action on the center is ergodic. But there's no exclusion that this C, this theta, okay, we will restrict the factor from now on, okay? In the factor now on. Now, I would like to emphasize that when you consider von Neumann algebra M, then what you should do is the following. Here's a miracle von Neumann algebra set on M, equipped with one parameter automorphism and tau. And M is M tilde fixed point. And I would like to emphasize, don't consider the cross product of M tilde by theta. Of course, this might give you the monitor equivalent for Neumann algebra, original algebra tensoring with L of L to R. But that's the, if you then you say, yes, type 3, M cross L of L to R, isomorphic to M. Isomorphic to M. It's not equal. Okay? So that requires, when you work on the problems, you have to work with the isomorphism all the time. Is it comfortable or not? That's up to you. I feel it is cumbersome to consider isomorphism all the time. So I rather consider realized and a fixed point. And very nicely, relative commutant in M tilde is center of original algebra M tilde, big one. And the relative commutant is, yes, that is the, here we saw. Now, one thing I would like to mention is the following. You consider what is M tilde, which considers the phi to the power it, one parameter unitary group, which is normalizer of M. sits in the normalizer phi t, that's giving rise to the modular automorphism of M. Now, if you consider phi to the power it for Neumann subalgebra, it is obviously this is abelian. I write it as upper phi, each sub phi indicate the centralizer. So A sub phi. How it look like? I have already discussed this one a bit. That theta S over phi it was e to the minus ist phi to the power it. Wasn't it? Yeah. Which means that phi s of phi equal to e to the minus. Immediately you recognize that phi cannot be bounded. Automorphism has to preserve norm, but at the same, norm has to respect scalar multiplication. So phi cannot be. At the same time, if you decompose that, then you can have that A sub phi equal to L infinity of R relative to Lebesgue measure. That's the uniqueness of Heisenberg commutation relation in the unitary form. You can consider this, okay, if you, well, theta is not unitary, but you can make it unitary considering cross product, the U of S, and phi to the IP satisfy the wire commutation relation. So it is unique, and it is L2R. And theta S of F of X equal to F of X plus S. If you do that, then you have no more choice. Phi of X has to be e to the minus X. It's a so unbounded element. And then C phi to the phi S of phi equal to phi of X plus S, which is e to the minus X plus S equal e minus S, e to the minus X. So suddenly this is e minus X phi of X. So it is given in that way. No other choice. Now, what happened with the following? Was it yesterday? I think I'm sorry that I have stated this one already yesterday. The unitary U of M tilde, U belongs to the normalizer of M, if and only if the co-boundary of U's of theta T over U belong to the center. Okay, this is not that difficult. Let me do it again. Because here, suppose you have this normalizer, U of U star. Let me see. Let's examine. U star theta T U and take X in M. M is fixed point under theta. So U star theta T X U. Then we have U star theta T U star X U. This is an identity. Now, this, wait a minute. Oh, yes. X, no. No, how come I write, this is, isn't this UX? There's no way to continue. X pops in because it is fixed under theta T. Pops in. And then this one is U star times theta T of U X U star U, because this is 1. Now, U is a normalizer. U X U star is an element of M. So it's hop out again. So this is U star, U X U star, and theta T U, and associativity U star U X U star theta T U. So this drops. This one commute with all X in M. So it is in the relative commutant. So it is a member of the center, if you believe this one. So also the converse is also similarly proven. Now, okay. But what is, however, the U star theta T of U? So this is central element of T. It's in the unitary of. It's being covariantly C of S of T equals CS right? So this is a cocycle. This C belongs to cocycle relative to theta. Coefficient is the unitary of the center. Okay. So it is a cocycle. Okay, need not be cobundary, of course. If U was chosen from center, then this is a cobundary. Yes. Now I consider the following little large algebra. I consider D of phi, which is A of phi join the center. But this is a stereo commutative polynomial algebra. Okay? And the C is L infinity of X nu. This is L infinity of R. And they join this commutative two polynomial algebra together. Then what you know is the following. When you have two commutative polynomial algebra, and okay, A1, A2, and commuting each other. So you can generate polynomial algebra A on the same space. It's then commute. How it looks like? Okay, so it needs not to be tensor product unless you are very but what you have is the following. This is arrow infinity of x1 mu1, and this is isomorphic to arrow infinity of x2 mu2. Joined, okay, then they exist. Measure mu on the Cartesian product x2 such that this A is L infinity of, say, x, the product, and the measure mu. In such a way, so this contains A. How? It is element in F in AA1 is F1 of x1, x2 is fx1, x1, x2 prime. Does not depend on x2 if original A1. It's constant along the second axis. And if you take element in F2, f of x1, x2 equal to f1, x1 prime, x2, namely constant along the first coordinate. That's the way you identify A1 and A2 within algebra A. Same goes here. Here is then, this one is L infinity of R cross X. That's the measure of, and you have, say, mu. The joint need not to be the product measure, which we don't need. You don't need a product measure, but it's, when you restrict to the one component, namely constant function along the second component, then you end up with the first. Okay, now, then I mentioned once about the Shapiro machine. Shapiro machine is a prescription to find the co-bounding element in your system. Okay. So and that's a well-known, it's a very good canonical procedure to locate which element co-bound. Okay, here, CST, so what matter? CS is Z1, okay, here's element there. CS is the element of A. Now, I define BC, B phi of C, Px, it will be, let me see how it works. I have to be careful, otherwise you don't get the co-boundary right. Well, let's try anyway. Well, is CP. And remember that's theta S of f of x on the center is f of ts my inverse x. Okay, so we use that p. I believe this is without inverse, that you cannot have much of a choice of the plus minus 1. Now, this is now, this VC is an element in the phi. It's an element in the phi. Now let's co-bound it. Okay, so co-bound B phi of C adjoint theta sub T of B phi of C and evaluate at Px. P is a real number. Oh. Okay, we take then this one, C of P, T P of X, adjoint, it's conjugate, and theta T, so this is a B phi of C of T, that means P plus T, and this is T to the inverse of X. Now, this is C of P, T, P, X conjugate. What was the definition of this one? You take C of this value times T of this TP plus 1. So this is C of P plus T, T, P circle T, T, and TT, inverse of X, waiting for me. So this TT, this disappear. So we have this equal to CP TPX times C over P plus T TPX. Okay. Oh, here's the conjugate. C over P TPX, the conjugate, cocycle identity of C over T. Wait a minute. Yeah, C over P TPX times C of T, the theta, this theta, remember S plus P equal to CP, theta sub P of C of S. So this goes into this other central element. So the T plus P, so CT plus the sigma P, that's theta P, TP inverse TPX. So this drops. So what remains is C of TX. That is your element. That's the co-boundary. Now what that is telling you? This co-boundary, remember on the far right, this is independent of P. When you move P, it's constant. So when you are in this setting, in this functional expression, if you move P along this constant, means this is an element in the center. That is an element C is C of T of X is in this unitary of the center. And that means that so this is a C of T. So C of T is then the one, or actually the one you are given, right? That's the original one. This is the original one. So this is B phi C sigma sub T of B phi of C. So what we obtain this is the following. B phi is a homomorphism from the co-cycle of the co-cycle group. I promised you I write the range always to the left, so I should continue to do that. So let me see. From the unitary of D phi. The homomorphism from here to there. And if you, and finally, this co-boundary goes into, well, what happened? Something funny happening. This co-boundary belongs to the center, means B phi of C is in the normalizer. You tilde of M, right? The co-boundary belongs to the center. And actually, the original co-cycle. So you have altogether B phi C is the normalizer of M. Add tilde of B phi of C. We write it, this is sigma phi C, called extended modular automorphism of the phi. So this is, okay, originally we had sigma phi, real line. Okay, the T goes to the e to the ist is a co-cycle indeed, being a representation, one co-cycle. So it is a very special case. If you check what you are happening, the B phi of this C of S, then B phi of C of S is indeed phi to the is. You end up with P first. Actually, you have an explicit way of writing B phi out of C. That's then so this is the extended modular automorphism. And if you work a little bit harder, then what you have is this. If you change the base phi to psi, then this B phi of C, B psi of C star, this will be the phi, the psi evaluated at cocycle C. So the Kohn cocycle derivative is now extended to the one cocycle on the flow weight. And because of this naturality of the construction of C, if you apply automorphism, then this is alpha inverse V phi of C alpha. So all natural thing occurs about the derivative, the cocycle derivative. If you have the phi circle, if you make alpha, then this is alpha inverse of the phi d psi of alpha inverse of C. Alpha of C, I think, here. The alpha has or if you like, this should be the mode alpha. The action on the center is mode alpha acting on. Everything coherent, thanks to the construction. Okay, I think we had worked hard enough, I think, today, including that equivalence relation, that quite a bit of confusion. Any question? I'm sorry, it seems I'm losing hearing power further, yeah?
Why is B phi C in U tilde of M?
What? B phi is U tilde because co-boundary belongs to the center. Remember the U tilde of M. U tilde of M is another way of writing is U tilde of M is those unitary in the U of M tilde such that co-boundary theta of U is in the center. In other words, U star theta T of U belongs to the center. And we had exactly that happens, right? When independent of P. And this was actually, well, the result itself is joint work with my former student, Tony Falcone. But extended modular automorphism of this nature, this one was considered in flow weight. But in that paper, we had to restrict to the dominant weight or integrable weight or very nice property on cocycle, such as this, the twice differentiable relative to t. And that's because when we work around myself, we considered M is M tilde. And we have control over tau hat. But here, because we are unable to reverse the point of view at the time in the 73, 74, we were unable to extend the modular cocycle modular automorphism to the general weight. Only those phi of this form. So that means actually strength of our strength is the viewing M as the M tilde the fixed point. And the phi appeared, the weight appeared all in equal footing. No privileged weight anymore. But in this writing, you have a very privileged weight. It's visible in front of you, tau hat, dual weight of the trace, which is not the right way, because you are giving special position to that weight, and indeed, we call that weight as a dominant weight. So we went to the dominant weight, and that dominate all pictures, and the others are subordinate, so it's hard. Okay. So this is the game out of this a bit complicated game, which is technically nothing difficult, but it's quite involved as you voiced in the equivalence class. But we had a harvest. So tomorrow on, everything is kind of a bonus. So we are now exploiting this canonical core. Well, there are several avenues to exploit, but there's just a few I'm going to do from tomorrow on. Thank you.